Okay, good morning, everyone. Let's dive right in. You're working on various assignments. Any questions about the assignments? Everything flowing relatively smoothly? Okay, all right. So we are going to finish up this morning. We are going to finish up Lecture 6 on physical simulation, which will finish up our second theme on tools of the trade.
Any chance we could talk about one of the quiz answers?
Let's talk about one of the quiz answers. Go for it. Yes.
For the collisions one.
Yep.
Why was there a +1 in the answer if we were ignoring the ground?
Why was there a +1? There's one additional collision that needs to be detected in addition to the 3 times 2 divided by 2 and the 4 times 3 divided by 2. Between the two groups. That's why collision groups exist. Most of the time, assuming this group is relatively far from this group, there only needs to be one collision detection, which is between the pair of bounding boxes around the collisions, which is the collision group. As long as these two boxes don't collide, none of these collisions need to be computed. That's why. It was a bit of a trick question on Tuesday. My apologies. Okay. Just to make sure you're paying attention. Another question.
I should ask this last class, but can you talk about the dimensionality question on the quiz from 2 classes ago?
Sure, yeah, the dimensionality question. So there was a question on the quiz from last week about fitness landscapes. Remember that the fitness landscape is a way to sort of visualize as best you can how an evolutionary process occurs. It was originally formulated back in the 30s to actually think about biological evolving populations. We can use it when we're talking about evolutionary robotics or evolutionary algorithms. The idea in a fitness landscape is usually it exists in a high-dimensional space, so it gets a little difficult to actually visualize it when we're talking about large dimensions. But imagine a space in high dimensions where every quote-unquote horizontal dimension, in 3 dimensions, there's 2 horizontal dimensions and 1 vertical dimension. Each horizontal dimension corresponds to one element in your genotype. If we're talking about DNA, that's individual nucleotides. If we're talking about vectors of numbers that encode synaptic weights for a robot's neural controller, we're talking about each element in that vector. If you're running an evolutionary algorithm with a genotype encoded as a vector, and that vector has length n, there are n horizontal dimensions in the fitness landscape. So far, so good?
Yeah.
Okay.
That was a Bradenberg vehicle, and there were like different like motors, synapses, and all of them count as different phenotypes.
All of the parts of the phenotype for the Bradenberg vehicle count that are encoded in the genotype. So if we're fixing the sensors and motors, and then we're connecting up this sensor to that motor with the synapse, that synapse has a weight associated with it, and that's what we're encoding in the genotype for the moment. So if we have 2 sensors and 4 motors, and we're wiring up every sensor to every motor, we've got 2 times 4 total synapses, 8 total synapses, which is 8 synaptic weights. Imagine we take those 8 numbers and embed them in a vector. That's our genotype. We're encoding 8 numbers for those 8 synapses. The corresponding fitness landscape has 8 horizontal dimensions, right? If we go to any point in that 8-dimensional space, that point is represented by 8 coordinates in space. That point in that horizontal space represents one and only one genotype. The particular settings or values for those 8 synapses. We take those 8 synapses, we run it on the Bradenberg vehicle, we see how well the Bradenberg vehicle does at whatever it is we want it to do, and that number that comes back from the fitness function, how well the robot did with those set of 8 synaptic weights, is the 9th dimension. It's the height of that point. So in a 2-sensor, 4-motor Bradenberg vehicle, we would have a fitness landscape that exists in 9 dimensions. Make sense?
Sorry, any chance you could review really quickly what the difference between genotype and phenotype?
Difference between genotype and phenotype. Genotype is a catch-all term for where the information is encoded. In us, that's your DNA. In the case of the Bradenburg vehicle we just talked about, the genotype is the vector. We talked about genetic programming, a particular type of evolutionary algorithm last time. The genotypes in genetic programming are encoded as trees. Yeah? The phenotype is when you take those numbers or that data that's stored in the genotype and you translate it into something and you make that thing go, and then you measure how well that thing does at whatever you want it to do. That thing is the phenotype. Phenotype normally refers to form and function. Your particular form and your function, whatever it is that you do. In most every evolutionary algorithm we're going to see, you're applying the fitness function to the phenotype, the robot, how well it does. And actually we're going to talk about two of the first evolutionary robotics experiments today, and you're going to see some different phenotypes. All good? Any other clarifying questions? Thanks for asking them. I want to make sure we're all on the same page as we move forward. Okay. All right, so back to tools of the trade and physical simulation. We ended last time by talking about collisions, yeah? Right. We talked about collisions. We ended last time by talking about collision detection. Just what happens when a collision event happens. In most physical simulators, there's some event-based programming, meaning that your computer's attention jumps to a particular point of code whenever a collision occurs. Now we're going to talk about collision resolution, which is how does the physics engine resolve a collision? Once a collision has happened, what does it do? Okay, first thing it does is check to see whether pairs of objects that have hit one another are supposed to be in contact with one another or not. If they're connected by a joint, ignore that collision event. If they are not attached with a joint, the physical simulation is going to have to try and resolve that collision. The way in which different physics engines resolve collisions is different. We're really getting down into the engine room of physics engines now. So I'm going to just sort of give you the basic intuition for how this works. And again, you can ignore the code, but for those of you that are really interested in physics engines, you can dig into the code a little bit to see how this works. Let's imagine we've got these two cubes, like the cubes in your tower from assignment 1 or 2. The physics engine has detected that these two cubes have come into contact with one another. The intuition is very much like what we talked about last week when a sphere is falling and comes into contact with the ground. The physics engine detects that collision between an object and the ground and applies an additional force acting on the objects. And those forces are going to try and push the objects apart. Makes sense, yeah? Okay. How does it do that? Turns out that it's actually tricky to get that right, to make the two objects hitting one another and then bouncing off one another. Trying to simulate that accurately is actually very difficult and requires a lot of computational effort. And as you recall from last class, we just talked about the fact that at a given time step in a physics engine, your physics engine might have to be resolving a lot of contacts. So it's in the physics engine's best interest to try and simulate this collision and rebound as accurately, but also as quickly as possible.
So in Hybel, when we have links connected by joints, one thing I noticed is sometimes they'll like fold into each other.
Yes.
So are collisions just never accounted for?
Great point. So all physics engines are accurate, none of them are perfect. And you can already see one obvious approximation we're making in the programming assignment so far, which you have these two cubes attached by a rotational joint, which means that the physics engine is ignoring collisions between these cubes because by definition, they're always colliding at every time step. The problem with that ignoring those collisions is depending on how they rotate, they can literally rotate into one another, which is very physically inaccurate. If you want, what you can do at the beginning of your final project, you can add in some details to clean that up and fix that, and we'll come back to that at some point. Okay, all right. So what do most physics engines do? They detect a collision and they know more or less where the collision has occurred. So in this case, the physics engine knows it's around here. Why am I saying around here? In order for the physics engine to detect exactly where a collision is occurring between pairs of objects, it's computationally intensive. So the physics engine, most physics engines cheat at this point. They know more or less where the collision has occurred, and they sprinkle a whole bunch of points into that region. And at each of these points, for one time step and one time step only, the physics engine creates a joint. Remember that when we talked about joints last week, we talked about the fact that joints restrict the relative motion of pairs of objects. My elbow joint restricts this particular body part from moving that way, while this body part stays here. Different kinds of joints restrict the relative motions between pairs of objects in particular ways. Contact joints, you'll notice there's some mentions of contact joints here, some mentions of contact joints back here. Contact joints are different from hinge joints. So joints, there's a whole bunch of different kinds of joints. Hinge joints are rotational joints, ball and socket joints, piston joints that cause two pairs of cylinders or rectangular solids to move relative to one another but not rotate relative to one another. Lots of different kinds of joints. This particular kind of joint, the contact joint, is temporary. At each point, the physics engine is temporarily kind of welding these objects together or is going to apply forces that cause them to accelerate. This object is going to accelerate away from this point, and this object is going to accelerate away from this point. These pairs of objects are also temporarily connected by this contact joint as well. So this cube is going to accelerate away from this point. This cube is going to accelerate away from this point. Yeah? Okay. In most physics engines, if you want to get down under the hood, you can set the number of contact joints that are spread by the physics engine into this estimated region of interpenetration, where these objects are either touching or already starting to collide. The more points you allow the physics engine to sprinkle, the more accurately it's going to resolve collisions between objects and figure out how they should rebound away from one another. But it's going to cost you. It's computationally intensive. Okay. Couple other details about collision resolution. There's some other parameters that are being set here called mu and bounce. You can set for these contact joints, which are restricting relative motion of the points. They're applying forces that cause these objects to decelerate and rapidly accelerate away from one another. You can set the exact way that these forces are applied to simulate different kinds of collisions. Imagine two rubber balls coming into contact with one another. Now imagine two steel ball bearings coming into contact with one another. Two pairs of objects, imagine they have exactly the same shape, size, and mass. Given their material properties, one pair are rubber balls, the other are steel ball bearings. The way in which they're going to rebound from one another is very different. And you can get down into the engine room of a physics engine and play around with that. As always, all of these nitty-gritty details are hidden from you. Okay. Collision detection and resolution is a tricky business. There's some things that can go wrong. What do you think can go wrong? Given what we've talked about, given the details of collision detection and resolution we've talked about so far, what could go wrong?
I mean, I kind of just think about, doesn't a sphere only really ever make contact at one point?
Do pairs of approaching spheres only ever collide at one point? Great question. In reality, in this physical universe, Yes. In a physics engine? I see Nate shaking his head no. Why not?
Because you have to get, so everything is divided into discrete slices. And so, the chances that you capture the exact moment where the two spheres are just kissing is unlikely.
Absolutely.
Probably just a little too late or too early.
Remember that regardless of the physics engine you're using, in a physics engine, time moves forward in discrete moments. And that discrete updating of time has huge repercussions for everything that happens in a physics engine, including collisions. We've got two objects that are moving towards one another, but the positions of those two pieces are teleporting actually a short distance during each time step. When you run the JPEG or you run the simulation, you don't see it, right? It looks like smooth motion, but like old-timey movies, there's actually discrete frames. It's your eye that's tricking you into thinking that there's continuous motion in the physics engine. There isn't. Which means, as Nate mentioned, you can have objects that are at time step t just separated, but at time step t+1, they are now overlapping by some amount. And the physics engine is not always exactly sure what that amount is. Again, with two spheres, it will sprinkle a whole bunch of contact points into that space. I saw there was a question. I just want to cycle back for a moment to contact joints. One detail that I mentioned, contact joints are the one and only type of joints which are temporary. The physics engine creates them during one time step. The physics engine using F equals ma uses those contact joints to apply additional forces that push the objects away at the next time step, during which all of these contact points are deleted again. Yeah, temporary joints. Question?
I was just going to say, so the discrete processing nature of the simulation, does that mean that errors accumulate over the simulation?
Absolutely, it means that errors accumulate over a physical simulation because we're updating time in a discrete manner, right? You're trying to simulate steel ball bearings, which in the real world absolutely do not ever interpenetrate. Right? They absolutely only come into contact with one another at a single dimensionless point, and it's at just that point that forces act to push them apart. It's hard to get that just right in a simulation, which means two objects that you're trying to simulate in a physics engine that are very, very rigid, that the way in which they move apart again after a collision is not going to be accurate, which means errors can start to accumulate. Absolutely. How do we rein back in that error accumulation, do you think, in a physics engine?
You modify the amount of physical time that passes for each.
Absolutely. So we mentioned a while back that there are a number of time scales that we need to juggle when we're running a physical simulation. One of those time scales is simulation time. The amount of time that elapses in the virtual world between one time step and the next. And in most physics engines, you can set that time step. If you set it to 0.1, that means 0.1 seconds of time elapses from one time step to the next. If you make that number very small, 0.00001, you still have a discrete simulator, but it's discrete like this rather than discrete like this. So why not just set the time step really, 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 really low? It's computationally expensive. So everything that goes, most things that go on in robotics that involve physical simulation and modern video games, they're trying to strike a very careful balance between physical realism so that errors don't accumulate and ensuring that the simulation doesn't take longer than the lifetime of the universe to run. Hard actually in practice to get these things right. Okay. So errors accumulate based on the discrete nature of time in a physics engine. How else can errors come in? They're ultimately because of this discrete nature, but what are the other things that can go wrong when you're simulating two objects that are moving quickly towards one another, for example?
they're moving quickly and the simulation time step is too large, you could literally just have them pass each other?
That's exactly the question, the answer that I was going for. Let's imagine you're going to simulate two bullets that have been shot at one another. You set the time step pretty low because you've got very high velocity moving objects, but they're still doing this. You can get into a situation in a physics engine where the two bullets do this, then this, then this, then this, then this. There was no collision detection and resolution. The objects never approached one another, or they never got close enough for collision resolution. So you often need to think carefully about not just the physical world, but what's going on in that physical world. Are some things moving a lot faster than others? What if you've got slower moving objects, but they're really, 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 really small? Same issue, right? Even if they're moving like this, but they're teeny tiny, there's a good chance that they could miss one another, and you've got some significant errors that are going to start to accumulate in your physics engine. Okay, none of this is probably going to be relevant for your actual projects, but just to give you a sense for some of the challenges in simulating robots and their environments accurately. Okay. Nate.
So we've already seen some examples where one object ends up embedded in another and just kind of flings itself off.
Yep.
I'm just, like, practically speaking, is that ever really a problem, or is that close enough to realistic behavior usually that we're okay?
Yeah, it's a huge problem. So if you've got parts of the robot that are interpenetrating and forces are being applied for the physics engine to pull them apart and they're flying off, none of that has a counterpart in reality. If you don't notice that that's happening and you try and take your evolved robot and instantiate it as a physical robot, you're not going to cross the reality gap, which we're going to spend a fair bit of time in this course talking about in about a month's time. How do you ensure that what evolution did in simulation transfers to reality? Very hard to get this right. Still a very active area of investigation. Okay, let's push on. Okay, I think we said enough about that. Okay, all right. Next thing we're going to do, we have our list, our usual list up here of all of the bits and pieces we want to build into our robot. Links, the parts that make up the robot. Joints that connect links together. Sensors and motors. Sensors, motors, neurons, and synapses. As I mentioned before, everything above this line is the responsibility of the physics engine. And we've just finished talking about most of those pieces in the physics engine. After today's quiz, you can safely forget all of these nitty-gritty details. What you're going to be doing in the sensors assignment and forward is adding additional stuff on top of what comes out of the box with the physics engine to allow it to simulate a robot. A physical simulator is not a robot simulator, at least not out of the box. You've got to add additional things. So how do we add sensors? Every sensor that you might add to your robot in this course, you're going to do so by exploiting stuff that the physics engine is already calculating. Let's start with one of the simplest sensors that are found in most robots. These are touch sensors or bump sensors. So I've got a sensor in this part of my body. This touch sensor is not firing, now it's firing, now it's firing, now it's not firing, now it's firing, and so on. So if I want to simulate a touch sensor, I could start adding additional code on top of the physics engine to look to see whether this object collides with any other object. It'd be an extremely stupid thing to do because the physics engine is already doing this for us. It's already detecting when pairs of objects touch one another. So if you dive into some of the pyrosim code, which is this additional code I've given you that sits on top of PyBullet. PyBullet is the out-of-the-box physics engine we're using in this course. PyBullet is some additional code that I wrote that's hiding some of these details from you. One of the things that pyrosim is hiding from you is simulating sensors. Pyrosim is dipping in to the contact points that the physics engine has already strewn within the volume of pairs of objects that are in collision during this time step. And we're then, PyroSim is writing some additional code that is looping through each of these contact points and looking to see if any of these contact points are associated with the desired link. If you say there's a touch sensor in this link, but not a touch sensor in this link, this piece of code runs during every time step of your simulation. This piece of code is looking at contact points, and if it finds a contact point that's inside a link that's supposed to be simulating a touch sensor, it sets something to 1. So it's simulating that sensor for you. So we're exploiting, PyroSim is exploiting stuff the physics engine is already doing to simulate, in this case, a touch sensor. Question?
So does that mean that the touch sensor only lights up for like one frame, or is it just like, it will just like keep finding the new contact point if things haven't like bounced apart?
Yeah, good point. So the only thing PyroSim will do for you is detect that the touch sensor has turned on. There's a collision that's occurred, and it's returning that value to you. What you do with that is up to you. You might want to simulate a touch sensor that fires and then immediately turns back off again. A lot of the tactile sensation in your skin actually works like this, right? There is pressure on your back and your underside right now, but you're usually not aware of it. You're usually aware of it for the first 1/10 of a second in the moment you sit in the chair, and then it kind of goes away again, right? So maybe you want to simulate a touch sensor that works in that way, or you want to simulate a touch sensor that stays on as long as the object is in contact with some other object. It's up to you, right? PyroSim is just trying to provide additional information for you, and what you do with it is up to you. Was there another question here? No? Okay. All right. Okay, so I'm going to just pause for a moment, and I want to put all of this stuff together so you can see how this works. Again, this is old C code from the physics engine we used to use in this course, but it should look relatively familiar to you now. We have this inner loop here called simulation loop. This simulation loop is running a number of subroutines, and in your case, these subroutines are sitting inside this for loop that you created all the way back in assignment 1. So you got a for loop somewhere that's looping 1,000 times. Each time it executes an instance of that loop, it's simulating one instance of time in over 1,000 time steps in your simulation. Yeah? So what actually is going on during each time step? In ODE, you would actually see this. Again, in PyBullet, this is hidden from you. The first thing the physics engine does is look to see if anything is colliding with one another and sprinkling these temporary contact joints between pairs of colliding objects. Every physics engine will then step the world, and step the world is shorthand for go to each object, look at all of the linear and rotational forces acting on that object, update that object's linear and rotational acceleration, and use those linear and rotational accelerations to update the position and orientation of that object. Then go to the next object, do the same thing, and do that for each object in the simulation, which steps the world. What's 0.05 here, do you think? The discrete time step. So in this particular simulation, the coder is telling the physics engine, step the physics by 0.05 seconds. All right, okay. Next thing ODE does, now that the world has been stepped, is throw away any temporary contact joints, if any were made. And assuming the graphics window is turned on, draw the current state of the world for the observer, and then rinse and repeat. One thing you can do, if you haven't done this already, is you can start to run your physical simulator in headless mode. Headless mode is slang for turn off all the graphics. Again, remember that there are multiple kinds of time unrolling in a physical simulation. There is simulation time, time 0, time 0.05 seconds, time 0.1 seconds, and so on. When you render the world, that's going to slow things down because your computer has to actually draw the graphics. So you might actually watch the frames, the visual frames, one after the other. Depending on the speed of your computer, those frames may be appearing on your screen faster than 0.05. Or if you have a very complex simulator with thousands of links and joints, each frame may actually be drawn in more than 0.05 seconds. Yeah? That's graphics time. And again, you're sitting there and watching that. Then we've got wall clock time as well. 3 different kinds of time that are unrolling during a simulation. Okay, all good? Okay. All right, so let's keep going. We're gonna put together a cartoon example where we're going to put all of these things, sensors, motors, neurons, and synapses, on top of a virtual robot. For those that have already got to the synapses assignment, my apologies, this is going to be a little remedial. For those that haven't got there yet, this is a bit of a preview for where you're going. Let's assume a very simple physical simulation that's only in 2 dimensions. We have a 2-legged robot here with a front leg and back leg and a main body, and there is some object that is out here in its environment. This little black dot and white dot are meant to represent 2 touch sensors. So we've got 1 touch sensor in this object and 1 touch sensor in this object. And as we just saw, we're going to simulate these touch sensors by piggybacking on top of the collision detection and resolution that the physics engine is already doing. So far, so good? We're just setting the stage for a moment. Okay. What if we've got our touch sensors here? Let's add in, just to practice, let's add in 1 additional sensor, which is a light sensor or a photo sensor. Remember Bradenburg vehicle 2A and 2B, the coward and the aggressor, that were detecting light levels? Let's say you want to simulate a photosensor in your simulation, and we're going to assume that this external object is actually a light source. It's emitting light. And we're going to place this photosensor in this particular object up here, object 1. You can see my code to do this. At every time step, I'm going to add in an additional subroutine that's going to simulate or update the value of this photosensor at that time step. In order to do that, I want to get the 3-dimensional position of this object, object 1, get the position of object 1. I'm going to get the position of this particular object out here, which in my numbering scheme is object 4. So get the position of object 4. And I'm going to now compute the light level of this photosensor as a function of the position, these 2 positions. Not surprisingly, I'm going to take the Euclidean distance between them and then take 1 over that Euclidean distance. The smaller the Euclidean distance between the light source and the photosensor, the more light is falling on the light sensor. The bigger the Euclidean distance between the photosensor and the light source, the lower the light level arriving at the photosensor. That should all make perfect sense. Yes? So I'm piggybacking on top of what the physics engine can already do for me, which is tell me what the current position of this object is and the current position of this object is. There's an additional detail here. I'm raising the Euclidean distance to the 2nd power. Anybody know why? Go back to your high school physics.
As the distance increases, the line intensity decays by 1 over r squared.
The light intensity falls off as 1 over r squared. So if I'm looking at this overhead light and I move twice as far away from it as I just was, the amount of light falling on my retina drops 4 times. If I move 4 times away, as I was before from the light source, the amount of light falling on my retina is 1/16. This is the inverse square law. It's just physics. So I happen to know that, and I'm putting that into my robot simulator. This is just, you don't need to remember the inverse square law. The reason I'm mentioning this is something that roboticists and people working on physical simulation do all the time. We try and put in additional details of the physical world so that ultimately, if we evolve this robot to perform behavior as a function of the light falling on the photosensor, and we take that evolved light-sensitive behavior, take it off the simulated robot and put it on a physical robot that operates in the real world where the inverse square law applies, we've got a better chance that that behavior is going to transfer.
What about line of sight or occlusion?
What about line of sight or occlusion, right? There's nothing in here that simulates that. So if this robot moving around ever comes, if an object ever comes between the robot and its light source, that evolved behavior is not going to transfer from simulation to reality. So let's go back in and elaborate the code that we use to simulate the amount of light falling on a light source at every time step. What happens if there's a shadow that falls on the photosensor? What happens if there's dust in the air? If we're prototyping a rover for NASA, there are certain planetary bodies where there's going to be significant dust in the air. That's going to definitely affect photosensors. Oh my goodness, that is not an easy thing to simulate in a physics engine. Things get increasingly difficult to simulate very, very quickly. 1 over Euclidean distance, trivial, 1 line of code. Inverse square law of light, trivial, 1 line of code. Simulating occlusion, not so trivial, 10 to 100 to 1,000 lines of code. Simulating dust and how it influences photosensors, somewhere to 500,000 to 1,000,000 lines of code. Things get really tricky really quickly.
At some point, you just like start looking to use like kind of a more mature like physics simulation that like has light already in it.
Absolutely. NASA is in constant contact with all the major games companies on the planet for exactly this reason. Trust me, you do not want to try and simulate how a dusty atmosphere influences a photosensor. But the good people at id Software have spent millions of person hours and coder hours simulating how to make sure that for a virtual camera inside a modern video game, that when there's dust in the environment, it looks realistic. And it turns out that that gets you 99% of the way to simulating that it's actually realistic. Not 100%, but gets you very close. Other questions? So far, so good? Okay, so we've got our simple 2-legged robot. We've got a light sensor in the body and touch sensors in the feet. Let's add in some motors now. And again, you don't need to memorize or remember this code here. This is C code from the old physics engine, ODE, but just to try and drive home this point. Remember that a motor, for our purposes, motors are always going to be attached to a joint, and the motor is going to send a value to that joint. It's the torque, the rotational force that should be applied, and forces act on links. So the joint is going to take that number, that torque, and send it to the pair of links that joint connects. And then the physics engine takes over from there. It updates the positions and orientations of the links, given that additional force that the motor is applying to the links through the joints. Let's imagine at this particular point in time, at a particular time step in the physics engine, the robot's front leg is off the ground, its back leg is on the ground. We've got a motorized joint at the shoulder here. And whenever, at time step 0, when a simulation starts, the angle of a hinge joint is always 0. This is a little confusing, and again, this is kind of an annoying part of physics engines. Intuitively, it looks like we've got this body part and this body part that are attached by a link here. You would kind of think that this angle is maybe 90 degrees. Doesn't matter what it looks like to you. The moment you create a joint that attaches pairs of objects together, the current angle of that rotational joint is 0. If I had created this robot by placing this front leg out, pointing out into the front of the body, out here, and again connected that front leg to the main body with a joint, the angle of that joint at time step 0 of the simulation is 0. It's confusing, I know. Okay. We're going to assume that fact going forward. We're going to assume that as the joint starts to apply torque, rotational force, to the pairs of objects that it connects together, that the angle of that joint changes. We're going to assume a particular way of describing this, where extension, meaning objects that rotate out and away from the body, those are going to be positive values. And flexion, meaning rotations of the joint that cause objects to move inward towards the body, those are going to be negative numbers. So positive numbers for extension and negative numbers for flexion. It's an arbitrary convention. We're just going to use it for describing all the different kinds of robots and physics engines we're going to see in this class. So far, so good? Okay, so at time step 0, theta is 0. We're going to tell this motorized joint that we want this motorized joint to rotate this object and this object so that this object extends away from the body. Extension, flexion in towards the body. We're going to tell the physics engine we want to extend this body part away from the main body by 60 degrees. It's an arbitrary number for the moment. I just kind of picked this out of thin air. Remember, a motor has a single value. It sends that to a motorized joint, in this case a desired angle. That joint takes that desired angle and turns it into a torque, rotational force, that's applied to the links connected by that joint. Okay, here's that in code. I am coding this up. I am telling this motorized joint, I want you to rotate your pair of links to 60 degrees. The code that follows, before it's got to take this desired angle and turn it into a torque. So it asks the physics engine, what is the current angle of the joint? And it takes the difference between the desired angle that I want and the actual angle that the joint currently has. In this cartoon example, we're assuming theta is at 0. We've just started the simulation, so actual angle is 0. The desired angle is 60. 60 minus 0 is 60. The difference between what I want and what currently exists in the simulator is 60. In ODE, the code that we're looking at, I would send that difference into the motorized joint, and the physics engine kind of takes it from there. It figures out an appropriate torque to apply. We're going to stop here and not go deeper into the code. So far, so good? Okay. You can probably imagine what that torque is. There's a pretty big difference between 0 and 60. So the physics engine at this point in time is going to apply significant rotational force to try and get this thing going. Okay, so it applies some torque, and at the next time step, that torque, remember torque is a force, F equals ma, the physics engine uses that force and the other forces to accelerate this particular, all the objects, but we're focusing on this particular object. So this object has now accelerated and changed its position and orientation. Remember, physics engines update position and orientation. So now the object is here, and the current angle of this joint is 20. It was 0, and now it's 20. I still want this joint to rotate this object to 60 degrees, extend this object out 60 degrees away from this object. So far, so good? Okay, so if we run this piece of code a second time during this new time step, what I want is still 60. The actual angle is now 20. The difference is less. It's 40. What do you think that does to the torque?
Reduces it.
The torque is less. Difference is less, so torque is less. So at the next time step 3, there's a bit of an error here. This object should now be moving, but moving less. We're applying less torque to rotate it to 60 degrees. Yeah? So if this angle was 0, then it was 20. At this one, it's probably like 38 or 39, right? It's still accelerating and rotating outward from the body, but it's slowing down because the motorized joint is applying less rotational force, less torque. Walk me through what happens over the next 10, 100,000 time steps if this piece of code stays constant. What happens to the front leg of the robot?
Asymptotically approaches 60.
It asymptotically approaches, right? It starts, the leg starts to kick out in front of the robot very quickly and very forcefully, and then it starts to slow down and slow down and slow down until it gets to 60 degrees. At that point, this difference is 0. The actual angle I want is 60. The desired angle that I want is 60. The actual angle is 60. The difference is 0. Apply no torque. What happens is this leg is hanging out in front of the robot at 60 degrees. Let's test our intuition about physics engines.
Sort of just wobbles back and forth.
It wobbles back and forth. Why does it wobble back and forth?
Because at one step it's 0, so it'll drop a little bit. But
Why does it drop a little bit?
because since it's 0, torque is being applied, so gravity will pull it down.
Remember that there are also other forces acting on this body, like you just mentioned. Gravity is always pulling it down, so it starts to droop or flex inward again, which increases this difference, which causes the motorized joint to apply rotational force to kick it back up again, and the front leg will probably wobble back and forth. Yeah? So far, so good? All right. That's motors. Okay. We've got sensors. We've got motors in there now. Let's connect up the sensors to the motors with some neurons and synapses. So we've got 2 touch sensors in this case. We're going to now ignore the photosensor for a moment. We've got a touch sensor in the back leg, a touch sensor in the front leg, and we're going to just focus on this one motorized joint at the shoulder. There's another motorized joint back here at the hip. We'll forget that for a moment. We've got 2 sensors. So inside, we're going to build the brain for our robot. We're going to assume it has 2 sensor neurons. And remember that sensor neurons just collect values from the sensors. At this point in time, the 2 sensor neurons are set to 1, 1 because the 2 touch sensors are firing. We've got one and only one motor neuron, M1 here. We've got 1, 1, and we're going to continue the example we just saw. We're going to assume that at time step 0, the value that arrives at this motor neuron is 60. To keep things really simple, we're going to ignore activation functions. Remember that activation functions sit at neurons and they squash values back towards some desired range. We're going to just ignore activation functions for our purposes today. What are the synaptic weights here? We've got 2 synapses that connect the 2 sensor neurons to the 1 motorized neuron. 30, 30, and 30, let's say. Makes sense, right? 1 times 30 plus 1 times 30 gives us 60. Yeah? So assuming we have a 3-neuron neural controller for our robot, 3 neurons and 2 synapses, and the 2 weights are 30, 30. Let's imagine we've got a genotype of length 2. We've got a vector that contains 2 numbers, the 2 synaptic weights, and the current values of that genotype are 30, 30. that particular pair of synaptic weights for this robot at time step 0 cause the motor to receive a value of 60. So we're now replacing this hard-coded code that I put in here. Imagine we delete this code and we're replacing it with a neural network. Now the motor neuron is talking to the motor, not my couple lines of code here. So far, so good? As we just saw, what happens, that causes torque to be applied at the shoulder, which causes the front leg to rotate off the ground, which at the next time step shuts this touch sensor off, right? So in robotics, we talk about sense, think, act. Here's sense. 1 plus 30 plus 1 times 30 equals 60. That's the think, sense, think. And then the act is the torque that's applied to the motor, which causes a change in the configuration of the robot. So at the next time step, this action has caused this sensory repercussion. The robot has pushed against its environment and observed how the world pushes back. This is a situated and embodied agent. Yeah? Okay. Now the touch sensor values have changed at this time step. The synaptic weights have not changed. We're assuming that the synaptic weights during these 1,000 time steps of the simulation, the synaptic weights stay constant. They don't change. The values inside the neurons are changing from time step to time step, but not the synaptic weights. There's no learning here. The strength of connections between neurons is not changing over the 1,000 time step lifetime of the robot. This is an important distinction between evolution and learning. When we talk about learning in this course, and usually in robotics in general, learning implies that the synaptic weights themselves are changing from one time step to the next in the simulation of the robot. Not happening here. No learning. We're just assuming there's some evolutionary process in the background that has set these two synaptic weights to 30. Turns out that these two synaptic weights are not actually 30-30. There's something different. If these two synaptic weights don't change, and when these two neurons are 1, the value arriving here is 60. When the value of these two neurons is 1, 0, the value arriving here is minus 90, a number I made up. What are the two synaptic weights actually?
First one would be negative 90, and the second one would be 150.
Absolutely. So we know here it's got to be 1 times x plus 0 equals minus 90. So x has to be minus 90. So this synaptic weight is actually minus 90, which means this synaptic weight has to be 150. 1 times minus 90 is minus 90, plus 1 times 150 is 60. Kind of arbitrary numbers for the moment. Question in the back.
Can you talk more about the difference between learning and evolutionary algorithm?
Yes, okay. Learning. We have this robot that's running around in its physics engine for, let's say, 1,000 time steps. We're just visualizing two different time steps here, time step 0 and time step 1. And we can see, even in this simple example, that the values at the neurons are changing from one time step to another. We're assuming for this simplified example that the two numbers sitting on the two synaptic weights, minus 90 and 150, we're assuming those two synaptic weights are the same at the next time step, minus 90 and 150. The synaptic weights are not changing. The strength of connection between pairs of neurons is not changing. Over the 75 minutes that you're sitting here and having to listen to me, strengths of connections between pairs of neurons in your brain are changing. You are learning. Hooray. That's learning. Changes in the strength of connection between pairs of neurons over the lifetime of an organism, or in our case, a robot. Okay. All right. So we've got minus 90. What's happening now? What happens as we keep unrolling this hypothetical simulation forward? Yes?
So it made it, looks like 20 degrees out,
Yes, so it's extended 20 degrees out.
and then it's the next time step, so it wants to go negative 90. Minus 20 is more 10.
Absolutely. So at this particular time step, the current angle of this leg, of this joint, is plus 20 because of what happened during the previous time step. It's extended out 20. The motorized joint is saying, I want a desired angle. I want a desired angle of minus 90. The difference between these is 110. Or actually minus 110. We're taking the desired angle and subtracting off the current or actual angle. What happens at the next time step, do you think?
It'll like make contact, but with the ground, and so it'll go back to the first one.
We've got a value of minus 110, a difference of minus 110 being sent to the motorized joint. It's going to apply a heck of a lot of torque. That's a big difference in flexion. Minus always means rotate in towards the body. A positive difference always means rotate outward away from the body. So there's a lot of rotational force that's going to be applied that's going to crank or torque that front leg back in towards the body, which means either at the next time step or at least very soon, this foot is going to come back into contact with the ground, which, as you said, means now we're back to this situation. The moment that front leg comes into contact with the ground, suddenly the two sensor neurons are registering 1-1 again. And because we're not changing the synaptic weight, that means that the motorized joint is going to ask for plus 60 again, which means now torque is going to start to be applied in the opposite direction.
Is there any potential of it to like kind of keep swinging through though?
There's also momentum in a physics engine, which we've kind of ignored for now. You're right. If there's enough torque that causes the front leg to accelerate inward towards the body, to flex inward towards the body, it might actually hit the ground and keep going. We're glossing over that detail for the moment. So the front leg started in contact with the ground, rotated out away from the body, suddenly started to rotate back in again and came into contact with the ground. What happens over the next 10, 20, 50, 100 time steps? Tell me about the robot. It moves how? At some frequency. There's an oscillation in the movement of the robot. When you walk, there's an oscillation. Most of the time, if you're not in a hurry, it's at about 1 hertz. Yeah? Where's the clock in here that's timing this motion? There is no clock in the physics engine, right? It's not actually timing this oscillation.
But it's the movement generated by the physics engine that creates the signal.
It's the movement that creates this oscillation, not just the movement. It's everything. It's the accelerations and decelerations, the momentum, the weight of the leg, the particular neurons and the synapses, the particular weights of the synapses are all set. We've got this sort of complicated system now, lots of different moving pieces that collectively result in this. If I were to hide all of this in the spirit of Valentino Breitenberg from you, I didn't tell you anything that's going on and you just watched the robot and I asked you how it was doing what it was doing, and you hadn't taken this course, you might give me an answer like, well, somewhere inside the robot, there's probably something like a metronome that's like counting off, and every time the metronome strikes, the muscles twitch in the robot, and it does this. Most of us would tend to attribute some explicit timer inside the robot, but when we crack this robot up, there's no one home. There is no timer inside. Remember our discussion about Breitenberg vehicles. I have emotions inside. I love, I hate. Breitenberg doesn't, it's just wires. I have free will inside. I have prospection inside. I can close my eyes and imagine what's going to happen an hour from now. I have retrospection inside. I can close my eyes and remember what happened on my last birthday. It's all in there. I can feel it. It's obvious. I have it. Machines don't. Maybe. Okay. Back to physics engines. Okay. All right. That concludes our discussion of physics engines and tools of the trade. Any questions about any of that before we spend 15 minutes on the very first years of evolutionary robotics?
Just with that diagram, when the leg swings out, would the robot not just like kind of topple over?
There's also that, absolutely, right? So there's momentum, the leg has weight. When it swings out, it might actually topple forward. This is obviously a cartoon example. Yes, lots of other things going on. You probably have a code base set up at the moment where with about half an hour of effort, you could probably knock something like this up and try it out. Can you set the synaptic weights so that you get your robot to do this? Can you set your synaptic weights so you get it to do this faster? Can you set the synaptic weights to cause it to do this slower? Give it a try.
Is it like more computationally heavy for a robot to learn than to be set by an evolutionary algorithm?
That's a great question. So is it more computationally intensive to get the robot to learn in addition to or in opposition to what we're currently doing, which is evolving the weights, setting the weights, and letting the robot do its thing? The jury is still out. I'm an evolutionary roboticist. I'll tell you, I would guess that in the final analysis, evolution is helpful. It's probably both, right? We evolve and learn. Ultimately, when we create useful and intelligent and safe machines, it'll probably be some combination of evolving the structure and the neural controller of the robot and also allowing the robot to learn, allowing the robot to change its synaptic weights as it moves around in its environment. Yeah, good question. Okay, all right, so onward to our history of the field of evolutionary robotics. The field of robotics as a whole, just as a reminder, has been around since the end of the Second World War. There are many, many different schools of thought and ways of approaching robotics and camps. We're talking about evolutionary robotics in this course. Evolutionary robotics has been around since about the early 90s. No, that's not what I want. So about 30 years. So we're going to go back and look at two of the very first evolutionary robotics experiments. The first one was conducted at the EPFL in Switzerland by an Italian researcher. So for our purposes, I'm going to refer to this as the Italian approach. An Italian doing a scientific experiment in Switzerland, a little confusing. We'll just call this the Italian approach. Okay, how did this work? This is the Kepra robot that they used in this experiment. The experiment was actually carried out a few years earlier. There were some prototypes of this Kepra robot that existed in the early 90s. Physics engines did not exist at this time, which means that how are these experiments going to be carried out? They're going to evolve this robot. In the real world, absolutely. Okay. The Kepra robot's about the size of a hockey puck. The nice thing about the Kepra, and there are versions of it that still exist today, is it's kind of stackable. It's plug and play. So there's the sort of drive train underneath, these two motorized wheels, one left and one right, and you can stack things on top. In this little grainy picture here, they placed a little gripper on the top, and this gripper can rotate down and close around a sugar cube and then lift that sugar cube up over its head. Sound familiar? Okay, all right. Nice thing about this hockey puck Kepra robot is you could perform experiments with it on a table and it wouldn't kill anyone. If it falls over, you're going to be okay. Okay. Here are some, arguably two of the most widely deployed autonomous robots on the planet at the moment. What's this one? It's the Roomba. This is the one that's actually a brush. I can't remember what it's called, but yes, the Roomba. Anyone recognize this one?
Warehouse bot.
It's a warehouse bot used by a particular company. Anybody bought anything from Amazon the last few days? If you've received a package from Amazon, it was probably moved about. Originally, that item that you bought was sitting in one of these vertical shelves. One of these little orange robots drove underneath and lifted up the vertical stack and brought it over probably to a human worker who then pulled out the item and put it in your box. The Kepra, not a lot of people have heard of it. It is the great-great-grandparent of a lot of the autonomous robots that are currently moving about on the planet. Okay. Here's a different extension. We just saw the gripper. We're going to actually look at the first evolutionary robotics experiment where they put a linear vision module on top of the robot. Not quite a camera. It's kind of a very crude camera. Sits on top of the robot, and at every point in time here in the real world, that little camera returns 64 numbers, which is the amount of light falling on these 64 photoreceptors. So not that different from a Bratenberg vehicle, and it covers about 36 degrees of coverage in front of the robot. Okay. How did they set everything up? No physics engine, so they're going to have to apply synaptic weights to the physical robot, let the physical robot run around on the top of the table for a few seconds, compute the fitness of that robot, go on to the next set of synaptic weights in the population, next set of synaptic weights, next. It's going to take a lot of time and a lot of effort. So what they did in this case was to tether the robot to a desktop computer, and the computer is going to run the evolutionary algorithm. It's going to, at the beginning, generate a random set of numbers, which are the random weights for the synapses. The computer is going to send those synaptic weights to the robot. I'm sorry, I misspoke. It doesn't say here. The evolutionary algorithm is running on the desktop. The brain of the robot is also running on the desktop. The desktop is going to take that set of random synaptic weights and apply it to the synapses of a neural network that's being simulated on the desktop. They're going to propagate the sensor value. They're going to get the sensor values back from the robot through this tether. They're going to plug those sensor values into the neural network, propagate those sensor neuron values through to the motor neuron values, get those motor neuron values back, turn them into torques, send those torques back along the tether to the Kepra robot, and those torques are going to be applied to the two wheels. So far, so good? Okay. All right, so what are the sensors? There was a little laser up in the corner above the table, and that laser would shine down onto the Kepra, and that would allow the Kepra or the system to take that the laser information and compute the XY position of the Kepra on the tabletop and alpha, the heading of the robot. So there are 3 sensor values coming in this hypothetical experiment. X, Y, and alpha, and then the neural network would say, given the current X, Y, and alpha, motorized wheels move like this. So far, so good? Okay, given that setup, what kinds of behaviors could you evolve for this little hockey puck type robot?
Maybe like basic navigation, like a 2D maze or something.
A 2D maze like this one. Yes, well done. Okay, all right. So this is arguably the very first evolutionary robotics experiment ever conducted. They built this simple 2D, it's not even a maze, racetrack on the top of a table. Remember I told you that there are these 36 numbers coming into this linear vision system. they put a little bit of code in place to take those 36 numbers and boil them down into 1, 2, 3, 4, 5, 6, 7, 8 proximity sensors. So as this little Kepra is moving around and starts to approach one of the walls of the racetrack, a light will actually drop. And it uses that drop in light to approximate proximity, how close it is to a source, to the wall. Okay, so we've got actually 8 different sensors and 2 motorized wheels. So the neural network controller, they've actually drawn it right on top of the robot. It might be difficult to see from the back, but we've got our 8 sensors, these gray boxes, and we've got 8 sensor neurons, the white circles. We've got 2 motors here, the white boxes, and 2 motor neurons, which are the 2 big circles in the center. 8 sensors, 2 motors. Every sensor is connected to every motor neuron. How many total synapses do we have? 16. Each of the 8 sensors is attached to each of the 2 motors. So imagine a genome, which is a vector of length 16. We need to come up with 16 weights for these 16 synapses, which is what they allowed the evolutionary algorithm to do. We're going to assume that the value that's sent from the motor neuron to the motorized wheel can be positive or negative. A positive number is the motor neuron trying to apply torque to the wheel to cause the wheel to move forward. A torque of 0 is causing the wheel to not spin, and a torque of -5 is causing the wheel to rotate backwards quickly. Yeah, so according to the synaptic weights, the wheels are going to start spinning forward, backwards at various velocities. Okay. We're going to assume that the 8 proximity sensors, or the values arriving at the sensor neurons, have a floating point value between 0 and 1. Proximity sensor is going to register a value near 0 if it really can't see anything. There is an obstacle 5 centimeters or further away, clear sailing. As the robot moves around and starts to approach an object closer and closer, that proximity sensor that's nearby is going to start firing with a larger and larger value. If that proximity sensor comes into contact with the wall of the racetrack, that proximity sensor is going to fire with a maximum value. Maximum proximity, 1. Okay. It might, again, may be difficult to see in the back of the room. You might notice that the synapses here have little arrows associated with them. And the sensor neurons that are attached to the ipsilateral, same side motor neuron have a particular kind of arrow associated with them. And synapses that connect from a sensor neuron to a motor neuron contralaterally, like this one, have a different arrow. These 2 different arrow types are representing that some of these synapses have been set manually by the researchers to be either excitatory or inhibitory. So in this experiment, the researchers are coming in and they're saying, listen, I have a little bit of an intuition for what these synaptic weights should be. Ipsilateral connections, they should have positive values. Whatever those weights are going to be, they should be positive. And contralateral synapses, those values should be negative. What the actual values should be, that's going to be up to the evolutionary algorithm. What is the intuition that the researchers are drawing on here?
That you want to move away from sources of contact.
You want to move away from sources of contact. So why do contralateral excitatory connections make sense?
Like the wheel on the other side would be spinning backwards, and the wheel on the side with the contact would be spinning forward and rotate the.
Sound familiar? Where have we seen this before? Bradenberg Vehicles was written in 1980, if I get now, 5 or 6, right? So 6 or 7 years before this experiment was done, these researchers did their homework. They knew that generally speaking, that's what you want, but what those actual values should be, who knows? Okay, we got 1 minute left in class, so let's think about how we're going to select for this behavior. We're going to evolve vectors of length 16. We need to come up with a fitness function where, as after a few seconds of the physical robot moving about in this racetrack, we want a function that returns 0 if the robot does the worst possible job, and a 1 if the robot does the best possible thing. Lower values are going to correspond to worse behavior. Values closer to 1 represent better values. In this particular experiment, the researchers built their fitness function from these 10 variables. They're assuming that they're going to get back from the robot the speed of the left and right wheel at a given point in time and the values of the 8 proximity sensors. We have 30 seconds left. Give me a general intuition. How do you combine these 10 variables?
You want to go as fast as possible, and then be the sensors to be the brightest, so they're farthest away from the walls.
Okay, you want the wheels to spin as fast as possible, and you want the proximity sensors to be as low as possible. Great.
Not fair enough.
Perverse instantiation. I know that isn't quite what you meant.
Yeah.
Work on it. See if you can write something down with pen and paper. We'll see you on Tuesday. You have a quiz due tonight. You're working on some set of assignments. Have a good rest of your week.